Okay, so let's continue with the Compton effect. So yesterday we stopped here, and we used the conservation of energy and conservation of momentum to derive a 1, 2, 3, 3 equation. And finally, if you try to eliminate some of the variables, then you'll finally get this equation for the Compton effect. So let's see how we can derive it. Let me just capture this free equation. Then here, okay. So we have a free equation, and actually we more or less need to eliminate the theta. You can see here, in this equation we only have a lambda, h, mc, and phi. We don't have theta here. Actually, you can simply imagine that we don't really care about the diffractive angle of the electron. We don't really care about this one. What we really care is the the scattered angle of the X-ray. So it is obvious we need to eliminate the theta. So the way for eliminating theta is very easy. I think you should have learned it in high school. So we should make use of the sine square plus cosine square equals 1. So we can just move the last term to one side and other terms to the other side. So for this one, we can have gamma mv cosine of theta equals h over lambda minus h over lambda prime cosine of phi. So this is the first one. And then for the second one, we move this term over. So we have a gamma mv sine of theta equals h over lambda prime sine of phi, like this. Okay, so in this case we can square both sides because we would like to have cosine square and sine square. So we just take the square on both sides for both equations. Okay, so in that case we can obtain gamma square m square v square cosine square of theta, gamma square m square v square sine square of theta equals the second one will be more easier. So it is h square over lambda prime square sine square of phi, like this. This first one is a little bit more complicated, but still is a minus b square is a square minus 2ab minus plus b square. So it is nothing but h square over lambda square minus 2 square h square over lambda prime cosine of phi, so 2ab, and then plus h square over lambda prime square cosine square of phi. So we take square on for both equations, and then we can just add them together. So on the left side, this term multiplied by cosine square and sine square, adding them together. So it is 1 for here. This is 1. So we have a gamma square m square v square. And then on the right side, we have this term. We have this term adding with this term, also sine square plus cosine square. So this is nothing but 1 times x square over lambda prime square. So finally we will have x square over lambda square minus 2h square over lambda prime cosine phi plus x square over lambda prime square. So this is the we call it equation 1. And yeah, and for the second one, we will make use of this one, this equation, which is from the conservation of energy. So we can see here we have a gamma square m square v square. Here we have gamma mc. So maybe we can just move this term to one side and the other term to the other side, and then take the squares to see whether we can simplify something. Because if you still remember, gamma square is 1 over 1 minus v square over c square, which is c square over c square minus v square. Yeah, like this. Okay, so maybe we try to rearrange the terms for this equation. We have gamma mc equals h over lambda minus h over lambda prime. And then here, gamma times mc, which is this one. And then minus 1 multiplied by mc, which is minus mc. Move it to the other side, which will be positive mc. Similarly, we take square on both sides. So we will get gamma square m square c square equals h square over lambda square. Oh, so this one is a bit more complicated. A plus b plus c quantity square is a square plus b square plus c square plus 2ab plus 2bc plus 2ca. So we will have a square plus b square plus c square, and then 2ab minus 2h prime, sorry, not h prime, h square, h square over lambda, this should be lambda prime, this should be lambda, okay, lambda prime, 2ab, 2bc is minus 2hmc over lambda prime, and then 2ca is plus 2hmc over lambda. Okay, so this is equation 2. Okay, so now we can try to subtract equation 2 by equation 1. So we have 2 substitute by 1, subtract by 1. Subtract by 1. So on the left side we have this one multiplied by this one. So we have a gamma square m square c square minus v square. Okay, so you can see if we just move this term to the left side, gamma square c square minus v square is c square. So this is nothing but c square. So this is gamma square m square, no gamma square anymore. It should be only m square c square, because this one and this one is c square. Okay. So on the right side, let's see whether we can eliminate something. So if we have equation 2, equation 1 is this one. Equation 2 is this one. Okay. When we subtract equation 2 from equation 1, we can see this one and this one are the same, so they are cancelled. Also, this one and this one are also the same. They can also be cancelled. Okay, so there are still remaining several terms. So the first one is m square c square. Okay, this is good. So these two terms can be cancelled later on. So this is the first one. And then we still have 1, 2, 3, 4. 1, 2, 3, 4. Okay. So yeah, let's see. So we have this one. We have 2x squared over lambda prime. 2x squared over lambda prime. So it will be something like 2x squared over lambda prime cosine phi minus 1. And then we still have this one and this one. So it is like 2hmc and then 1 over lambda minus 1 over lambda prime, like this. Okay, so now maybe we can just remove this one. So now we can see that mc square and mc square can be cancelled. And then the remaining terms is this one and this one. So we can just move it over. And then we also try to multiply lambda prime on both sides. Because the left side is 0, so it's nothing. And then we try to move this term to the left side. So it becomes, and also you can see that 2 and 2 can be cancelled. H and H can be cancelled. So we can further simplify it a little bit. So now we can see, we move this term to the left side, so it becomes H, lambda and lambda pi can be cancelled. So it becomes H times 1 minus cosine of phi. And then this term distribute inside, so it becomes mc and then times lambda prime minus lambda. And lambda prime minus lambda is the delta lambda. So this is nothing but mc times delta lambda. So finally we have delta lambda equals h over mc times 1 minus cosine of phi. Okay, so we get this, which is actually the same as this one, of course. And here we call the h over mc to be the quantum wavelength. It is actually a constant for a specific particle because h is a Planck constant, which is 6.63 times 10 to minus 34. And then c is the speed of light, also a constant. And m is only related to the mass of the particle. For this one, it is an electron. So for a specific particle, then it should be a constant. And it is inversely proportional to the mass, which means that the lighter the particle is, the wavelength is longer. So you can really imagine if for a particle with mass, the electron is already the lightest particle. You just ignore something like the photon, which is massless. So yeah, so here electron is already the lightest one, so which has the longest quantum wavelength. It should be the most the easiest quantum wavelength to observe. Okay, so here we have a sample problem. So it says X-ray of wavelength lambda equals 22 picometer, photon energy 56 kilo eV are scattered from a carbon target, and the scatter ray are detected at 85 degrees to the incident beam. What is the quantum shift? Quantum shift means the delta lambda of the scatter wave. So this is easy. We just need to plug in the equation, plug in the values to the equation. So delta lambda is h over mc times 1 minus cosine of phi. Okay, so h is nothing but 6.63 times 10 to minus 34, and then m is 9.11 times 10 to minus 31, and then c is 2.998 times 10 to the 8th power, and then times 1 minus cosine of 85 degree. Yeah, because it's only asks you the scattered wavelength or the quantum shift at this angle. Okay, so we need to use the calculator to find that the delta lambda will be 2.2 picometer. So this is the incident wavelength, and the delta wavelength is delta lambda is 10% of it. 10% of it. And of course 10% longer, because you always lost energy to collide with an electron. And then what percentage of the initial X-ray proton energy is transferred to an electron in such scattering? So there is some energy loss. What is the percentage? So the fraction of energy loss, fraction of energy transferred equals, originally the energy will be HF, and then after the collision is HF prime, and then considering fraction, the denominator should be the original energy. Okay, and then so we can just cancel all the H are all cancelled. And of course now we know the wavelength, so we try to use C equals F lambda. So we can change F into lambda, so that we can have a C over lambda minus C over lambda prime all over C over lambda, and then C can also be cancelled. C are all cancelled. So finally it can be simplified to be, so you just multiply it by lambda prime, and then lambda prime. So it becomes lambda prime, and then here lambda prime minus lambda. So this is delta lambda over lambda prime. So which is 2.2 over 22 plus 2.2. So this is 9.1%. Okay. So the wavelength is 10% longer, but the energy is only 9.1% of the energy is transferred to the electron due to the scattering. Not due to the scattering, to cause the scattering. Yeah. Okay. So here we start to enter the quantum mechanics, and here it presents a very complicated concept called the probability wave, 几率波, light as a probability wave. So the probability per unit time interval, that a photon will be detected in any small volume and center on a given point in a light wave is proportional to the square of the amplitude of the wave electric field vector at that point. Yeah, this is hard to understand, but yeah, here it mentioned it recap an experiment called the double slit interference. Of course, in this semester we just give the chapter 35. We actually skip chapter 34, 35, 36. Yeah, skip those 3 chapters. Actually, those are some optics which you should have learned it in high school, so I don't bother to repeat it again, because it's difficult to talk more forwardly. But actually you may be learn something more interesting. So actually in high school you should have learned the double slit experiment, and suppose here we have something like a wall, or this B is like a block, so there are plane wave incident to the right side, and there are two slits. Should be very close together, but it's just draw it separately. But actually, these two slits should be close together. And then finally, there will be some interference pattern on this monitor. So, and of course, this experiment is to tell you that the light should have the property of wave, because some of the position has the superposition. Some of the position is cancel each other, so that they are peak, equal distributed on the monitor. Actually, if you would learn something called the Fourier optics, actually this one is related to the Fourier transform. Fourier optics. You can imagine in signal and system, if you have a cosine of omega t, you take the Fourier transform. You have something like delta omega. Maybe this one is called omega 0, omega or minus omega 0, and then plus delta omega plus omega 0, and then all over 2 pi. All over 2 pi. It should be like that. Okay, and you take the inverse Fourier transform, or you take the Fourier transform again, you only multiply by a factor. So it's just like if you have delta function in the time domain and then take the Fourier transform again, and then you get the cosine. So you can see here, you can imagine this is a delta function. This is a delta function as the source. And then the wave passed through this slit is like having a Fourier transform in a physical way. And then this one is the Fourier transform of these two delta functions. So this is a cosine function here. See, so this is the so-called Fourier optics. Yeah. Okay, so this is a way to if you were able to learn something called the Fourier optics, it would be something like that. Okay, but just go back to here. So the probabilistic description of a light wave is another way to view light. It is not only an electromagnetic wave, but also probability wave. That is to every point in a light wave, we can attach a numerical probability per unit time interval. Wow, so it's so complicated. It looks so complicated, but yeah, let me try to talk something about the probability. Of course, in high school, you should have learned something like the probability combination, something like that. But yeah, if you will learn a course in bachelor degree, the probability course, you will learn something called the random variable. So random variable is something like, so for probability, you should be able to learn something called a random variable. Random variables. Okay, just imagine you have a dice. You have maybe called 1, 2, 3, something like that. I'm not sure which one opposite to get. So when you throw a dice, if it is a fair dice, then you should be able to get 1, 2, 3, 4, 5, 6 with equally probability to be 1/6. So which means that maybe we can define a variable called x is the outcome of throwing a dice. So x can be 1, 2, 3, 4, 5, 6. So you say, oh, it's just stupid. But actually, in probability, we will be able to write it like something called a probability mass function. Probability mass function, which is like px equals x to be 1/6 for these dice, and x will be able to be 1, 2, 3, 4, 5, 6. Okay, so it looks so complicated, but actually it mentioned that if this random variable equals to 1, then the probability, this means the probability of this event to occur. So this is the probability of this one equal to 1 will be 1/6, equal to 2 will also be 1/6, so on and so forth. And maybe you can write something more complicated, maybe like if you throw 2 dice and then the sum of the outcome, we denote it as y. The sum of the outcomes of throwing 2 dice. Throwing 2 dice is okay. So in high school, you should be able to know y could be 2, can't be 1, because at least it would be 1 plus 1. So 2, 3, up to 12. 6 plus 6 is 12. So the probability of y equals small y will be like 1/36, 2/36, up to something like 7/36, and then going back 1/36. This is y equals 2, y equals 3. This one should be no, this one should be 6/36. Y equals 7. Y equals 7. This is y equals 12, or something like that. So because for 2, it can only be 1 plus 1, but for 3, it can be 1 plus 2, 2 plus 1. So there are totally two cases for that, and so on and so forth. The most probable case is y equals to 7, which means 1 plus 6, 2 plus 5, so on and so forth, up to 6 plus 1. So yeah, so we will define something called the probability mass function to describe some random event. And of course, if the outcome might be continuous, so there will be something called the probability density function. Probability density function. So in short form, it is a PDF. Not the file type. Actually, it is called PDF. This is PMF. So this is for continuous event. Continuous event. Maybe you try to throw. There is a dartboard, a 飞镖靶. Maybe there's a dartboard, and then there is something like I played for several times. Something like that, and then you throw a dart on it. So maybe when you throw one on the dartboard, there should be a coordinate axis. Maybe this is 0, 0, and then x-axis, y-axis. And then after you throw a dart on it, maybe you throw it here, then there will be x, y coordinate. This should be random. Before you try to throw it, then it is random. After you throwing it, there's an outcome. Then this outcome should be continuous. And yeah. It may be 10 meter, sorry, not 10 centimeters, or maybe 1 centimeters, 1.5 centimeters. It should be a continuous value. Okay, and this probability density function should be a Gaussian function. So which would be like exponential to minus x minus mu square over 2 sigma square, and then 1 over 2 pi square root sigma, something like that. This should be the Gaussian distribution, or we will call it the normal distribution. 常态分布是这个式子。Okay, so there will be something called the probability density function, probability mass function, to describe some of the random event. And actually, for the quantum world, we will not say, the particle is there, the particle is at this point, at this moment. We will not say that. We will say there will be a probability density function that the particle is at this point or this moment. But actually, you don't really know where it is actually is. Just say when I say I'm in a, just say, for example, if I go to八百伴, just say, maybe a friend call me and ask where I am. I tell him, I'm at 八百伴. And I'm not telling lie. Actually, I am within the area. So there will be a probability density function. I am going to somewhere, maybe just looking to the toys, maybe looking for the shoes, or looking for something, or maybe I just go to the toilet. So there will be a probability density function. Or maybe during the weekday, I will be mostly at my office. So I will also have a probability density function. I will be most probably in my office. And actually the position of me might not be a fixed point, because even though I'm sitting here, the position, the coordinate of me is moving. Actually, sometimes I will be leaning forward, sometimes I will be going back a bit. So there will be a variation. My position is actually changing. So if I am not having lecture, I will mostly be at my office. Maybe I'll go to the toilet of N21. Maybe, so maybe sometimes I'll go to have lunch somewhere. And of course, for this moment, I'll mostly be at the classroom. So Tuesday morning, I'll be at 10227, and today I'll be 1025. And it is time varying. For different time, I will have a different wave function to define me. So so this is the point for having the probability density function here. Okay, so it says the light as probability wave, and of course later on we will also describe something called the wave function, 波函数. Actually, you may have learned this term before, although you may not know what it actually is. And of course, solving the Schrödinger equation will have the solution as the wave equation. Actually, the interesting point, or the most annoying point, is that the wave function does not have any physical meaning. This is a strange thing, but it is useful. The one interpretation for the wave function is called the Copenhagen 的解释啊 Copenhagen interpretation is that when you take the absolute value of the wave function and then take the square, it will become the probability wave of the particle. So later on we will have this is the wave function. This is the wave function. And then for the Copenhagen, I don't know how to spell, but Copenhagen interpretation. You take the absolute value and then take the square. It becomes the probability density function, maybe in X, yeah. So something like that. And this makes the Schrödinger's equation very useful, because actually you cannot try to prove why Schrödinger's equation is correct. You cannot derive it out. You can only use some assumption to try to write it out using some classical mechanics understanding, and then use some assumption for the quantum mechanics, and then you write out the Schrödinger's equation, but you can never prove it to be correct. But the interesting point is that the Schrödinger's equation you can solve the Schrödinger's equation for some solution, for some specific case, and then it can predict the phenomenon very precisely. So that's the interesting point. That's an interesting point for the quantum mechanics. But actually, this is very complicated. Okay, so there are many texts, so I feel like I should skip through it. Okay, so here it says light is a probability wave. Light is a probability wave. So you may still consider, the light is a photon, is a particle. So maybe we should be able to define the position of it correctly, just like what we have done in the classical mechanics. For the classical mechanics, if you have an object, you know the mass, you know the force acting on it, then you will be able to calculate its locus very accurately using the Newton's second law of motion. F equals ma, just like F equals m times d2x dt2. Yeah, the second derivative of the displacement multiplied by the mass is the force. And if you know the force and know the mass and know the initial condition of the object, then you will be able to draw the differential equation governing the object. And then when you solve the differential equation, you will be able to know the locus of it. You know the displacement of the object at any time after the initial moment, and then you will be able to know the velocity, know the momentum, know the energy, kinetic energy, so on and so forth. You can, according to the mindset of the classical mechanics, you should be able to know the object, how it moves very precisely. But actually, quantum mechanics tell you that's not the case. This is the experiment. This is one of the experiments to really show this interesting stuff. Actually, you can see here, this is a paper in the Journal of Optical Society of America in 1992. 1992. Of course, you are young, so probably you are after 2000, but actually not. So it's quite close to us. 1992, just less than 30 years ago. This year is only 2021, so 29 years ago, having this experiment. It says a single photon can take widely different paths and still interfere with itself. So this is an interesting phenomenon. So you may say the interference is due to different photon, the interference at the same position, then there will be interference phenomenon. But actually not. It tried to shoot out a single molecule, 一个分子 from the source in two paths. There will be two paths, one path 1 to here. There is a mirror here. and then there's another mirror here, and this is pass 2. So of course this is totally symmetric, which means that when the particle go from here to here, and then go from here to here, then they will overlap at the same point, and the case is it only shoot out a single molecule, but actually it has interference here. It has interference in here, which means that there is maybe 50% of the molecule going in this path and 50% of the molecule going in this path. Actually, this single molecule go in the two paths simultaneously and then interfere with itself. And then there are interference pattern detected here. Yeah. So this is a crazy idea. We can never understand. So the light from a single photon emit in source travel over two widely separate paths and interfere with itself at detector D after being recombined by the beam splitter. Yeah, so here we assume that the light is generated in source as a photon. So here at the very beginning is something like a photon, is a particle, and then the light is absorbed in the detector also as photon. But actually in between, the light travel between the source and detector as probability wave. So this is wave. Actually within this single setting, both the particle and the wave property occurs here. So this is probability wave here, and then photon, something like this. And so far we just talked about the wave for the photon, and next we'll try to talk about the matter wave, and then maybe let's have a 10 minutes break first.